Hello everyone, welcome back. Today we will look into the different traversal techniques used to visit all the nodes in a binary search tree. This same traversal techniques we have discussed in a detail in our previous videos for binary tree, and these techniques are used for binary search tree also. So we will cover the same techniques with some additional points for binary search tree in this video. So in a depth first traversal, we will cover preorder, inorder, and postorder. And in breadth first traversal, we will cover level order traversal. Let's understand the preorder traversal. So in a preorder traversal, for a tree, we visit the root first and then explore the left subtree, and after that go for a right subtree. Let's understand with this example. So for this whole tree, 50 is a root. So we visit the root, which is 50, and then go to the left side, which is this one. So we visit the left side. Now for this left subtree, 30 is the root. So we visit the root 30 and then go to the left side of it, which is 20. So for this subtree, 20 is the root. So we visit the root. Now there is no left subtree. So it will go to the right side. There is no right subtree. So basically it will backtrack to 30. So for 30, we have completed the left side. Now we'll go to the right side. So for this right subtree, this 40 is the root. For this 40 root, there is no left side, there is no right side. So we'll visit the 40, we'll go back to the 30. Now for 30, left subtree and right subtree is visited. So we'll go back to the 50. Now left side of this tree is completed. Now we'll go to the right side, which is 60, and we'll visit the 60. So this is how the pre-order traversal works. Basically start with the root, then go for a left side, and then go for the right side. Let's understand the pre-order traversal implementation. So this is the tree node class, which represents the node of the tree. Value is the data in the node, and left and right are a pointer to left child and right child of the node. So this is the pre-order traversal function. It is a recursion based implementation. So we'll show the system stack here. So initially pre-order function will be called with the root of the whole tree, which is node 50. So node 50 is a root here. Now we will visit the node, this based on this print statement. Then we'll go to the left side of it. Visit the root and then go to the left side. So pre-order will be called with the node 30 as a root. So now pre-order function is executing with node 30 as a root, basically for this subtree as a tree. So we'll visit the root, which is 30 now, and then go to the left side of it. So the pre-order is called with the node 20 as a root. So the pre-order function is executing with the node 20 as a root, this subtree. So we'll visit the root. We will go to the left subtree of this tree, which is root.left, which is 20.left. It is null. So it will basically return. It will return to the next statement. So pre-order root.right will be called, which is 20.right, which is null. So it will again return back, and the pre-order function for the node 20 as a root will complete. So it will come back to the previous function execution. So for node 30 as a root, we have completed the left side. So it will basically call the pre-order now for the right side, which is 30.right. So pre-order will be called for node 40 as a root. So we'll print the node 40. We'll go to the left side, which is null. So it will come back. We'll go to the right side, which is also null. So it will come back. And it will complete the pre-order execution for the node 40 as a root. And it will basically backtrack to pre-order function execution for node 30. Backtrack here because we completed the left and right. So for node 30 as a root, that pre-order function execution will now finish. And it will backtrack. Where it will backtrack here for the pre-order function execution with node 50 as a root. We have completed the left side. Now it will call the pre-order with root.right, which is 50.right. So pre-order is called with node 60 as a root. It will print the root. It will go for the pre-order root.left, which is 60.left, which is null. So it will return. Then it will go for 60.right. That is also null. So it will return, and it will backtrack to the previous function execution, which is pre-order node 50 as a root. It will come back here. Now we have completed the left side and right side. So the pre-order function execution with node 50 as a root is also completed. So this is how the pre-order traversal implementation works for binary search tree. So let's understand the in-order traversal for binary search tree. So in order traversal, for each node, we visit the left subtree of that node first, and then visit that node, and after that we visit the right subtree for that node as a root. So let's understand with this example. So we'll start from the root of the tree, which is 50. We'll go to the left side. We'll keep on going to the left side, and now we came to this subtree where 20 is a root. For this 20, there is no left side, so now we will visit the 20. Then go for a right side. So the right side there is nothing, so it will basically backtrack. So for this 30, we have completed the left side, so we'll now visit the root. Left is done, so we'll visit the root, which is 30, and then we'll go to the right side. So this is 40. So for 40, there is no left, so we visited the 40. There is no right, so we'll backtrack to 30. So for 30, left and right is done, so we'll backtrack to 50. Now for 50, left side is done, so we'll visit the 50, which is root, and then go to the right side of that 50, which is 60. For 60, there is no left, so we visited the 60, and then went to the right side of the 60, which is also null, so it will basically backtrack. So basically, this is how the in-order traversal looks like. We start from the root of the tree. We don't visit it. We keep on going on to the left side. And once we complete the left side, we go to that root, visit it, and then go for the right side. So if you observe one thing, the in-order traversal of binary search tree gives us the elements in a sorted order, right? 20, 30, 40, 50, 60. So you can see we got the elements of the binary search tree in a sorted order. So keep in mind that the in-order traversal on a binary search tree gives the output in a sorted order. Why? Because it is going on a left side first. Now the smallest element will be on a left side of the binary search tree, and then it is going to the root side. After the left side, the next greater element will be on the root, because for the root, the smallest elements are on the left side and greater elements on the right side. So we visit the left, which is the smaller element, and then go for the root, which is big element than the left side, and then we go for the right, so which is the greater element than the root. So basically we are visiting the elements in a ascending order. That's why in-order traversal gives us the output in a sorted order for binary search tree. Now let's understand the in-order traversal implementation. So this is the same tree node structure, which represents the node of the tree. So this is the in-order recursive function. That's why we are representing the system stack here. So in-order will be called with the root of the tree first, which is node 50. Now we are not visiting the root, we are going to the left side of it. Now 50 root dot left is 30, so in-order will be called with the node 30 as a root. So for this subtree, for this root 30, we'll go to the left side, which is 30 dot left is 20 here. So in-order will be called with node 20 as a root. So for node 20, it will again go for left side. So for node 20, there is no left, so it will basically return because it is a null. Return where it will come here because we completed the left side for node 20. Now we'll visit the node 20 and then go for the right side of it. So right side is also null, so we'll come back and complete the in-order function execution for node 20 as a root. Where it will come back? It will come back to the previous function execution, which is in-order with node 30 as a root. It will come here because we completed the left side of it. So the recursion will come back here. Now we will visit the node 30 because we completed the left side of it. Now we'll go to the right side of it, which is 40. So in-order will be called with node 40 as a root now. Now for 40, there is no left child because 40 dot left is null, so it will return. It will basically print the root dot value, which is 40, and then it will go to the right side of it, which is null, so it will come back again. So the in-order function with the node 50 as a root for this subtree is completed. We will come back to the previous inorder function execution, which is inorder function execution with the node 30 as a root. So it completed the left side, visited the node, and completed the right side. So it will complete the inorder traversal for this subtree where 30 is a root. So it will come back to the previous inorder function execution, which is for this tree where 50 is a root. So we completed the left side. So it will come here and it will print the node 50 value, and it will go on to the right side of it, which is node 60. So inorder is called with the node 60 as a root. For node 60, there is no left. So it will basically return. Now it will print the 60 value and then go for the right side of it, which is also null. So it will come back and then complete the inorder function execution for node 60 as a root. And it will basically come back to the previous function execution, which is the inorder function execution with node 50 as a root for this whole tree. So it completed the left side, visited the nodes, and completed the right side also. So it will complete the inorder traversal for the node 50 as a root. So we completed the inorder traversal for whole tree. And this is how the inorder traversal implementation works for binary search tree using recursion. It is similar to binary tree only, but only difference is that output is basically the sorted elements of the tree. The inorder traversal output is sorted elements of the tree, ascending order. Now let's understand the post-order traversal. So in a post-order traversal, we visit the left subtree first, and then right subtree, and then finally visit the root. So let's understand with this example. So we'll start with the root of the tree, which is 50. We'll go on to the left side. So for this left side, there is a left child, which is 30. So for this 30 as a root, for this subtree, we'll go to the left side, which is 20. For the subtree with the 20 as a root, there is no left side. So we'll try to go to the right side. Now there is no right side. So we'll go to the root, which is 20. We'll print the 20. Then we'll backtrack. Now for this 30, there is a right side. So we'll go to the right side. We'll visit the 40 because there are no left and right for 40. Now we'll come backtrack. Now for 30, we completed the left and right side. So we'll visit the root now. So which is 30. Now it will backtrack. It will come here. Now for 50, we completed the left side. So let's go to the right side, which is 60. It will print the 60 because there is no left and right for 60. It will backtrack. Now for 50, we have completed the left side of it and right side of it. Now we'll visit the 50 root. So this is how the post-order traversal works. Basically, we'll start from the root, then go to the left subtree, and for each left subtree will follow the same thing. Go to the left and then go to the right and then visit the root of that tree, or basically the subtree. Let's understand the implementation for post-order traversal. So this is the post-order traversal function, which is also we have implemented using the recursion. That's why we are showing the system stack here. So the post-order will be called with the node 50 as a root, which is the root of this whole tree. Now we'll go on to the left side. So what is the 50 dot left, which is 30. So post-order is called with the node 30 as a root. So now the post-order is executing for this subtree where 30 is the root. Now 30 dot left is 20. So it will call the post-order with node 20 as a root. So this is the tree for which post-order is gets called with the node 20 as a root. Now we'll go to the left side of it, which is null. So it will come back. Now it will call the post order 20 dot right, which is also null. So it will come back. It will come back here. We will visit the 20 and that complete the post order traversal for this subtree where 20 is the root. It will backtrack to the previous post order function execution. Left is completed, so it will basically go to the right side of it. The post order function execution with node 30 as a root. Left is completed, so it will go to the right side. So post order is called with the node 40 as a root. Basically now for this subtree, it will go to the left side of it, which is null, so it will come back. It will basically go to the right side of the 40, which is also null, so it will come back. It will print the 40 and then complete the post order traversal for node 40 as a root. And it will basically backtrack to the previous post order function execution, which is for the tree with the 30 as a root. Now left is completed, right is completed, so the call will come here. So we'll print the 30 and backtrack because post order is function execution for node 30 is completed. So it will backtrack to the previous post order function execution from where we had called this post order for 30. So it will come here now because left side of the 50 is completed. So it will go to the right side, which is 60. So it will call the post order with node 60 as a root. So for 60, it will go to the 60 dot left, which is null. So it will return. Then it will go to the right, which is also null. So it will return, come back here, it will print the 60 and then go back to the previous post order function execution, basically backtrack the recursion. So where it will come to the post order function execution with the node 50 as a root, because from there only we had called the post order 60. It will come here, the next line. So for the 50, we have completed the left side and right side. So we'll visit the 50 now and print it and basically complete the post order traversal for whole tree where 50 is a root. So this is how the post order traversal implementation works for a binary search tree. So we saw that pre-order, in-order, post-order traversal, the implementation is similar to binary tree only. Only thing is how the output is printed for different traversals, like in order. It is the special order which is followed for a binary search tree, like ascending order output. Now let's understand the breadth first traversal for binary search tree. So level order traversal. So in a level order traversal, basically the tree is divided into the different levels and starting from the root of the tree. So the first level is visited and then next level is visited and then next level is visited and so on. So this is the level order traversal. So because it is a part of breadth first search traversal, so that's why we will use the QU here. So this is the implementation for level order traversal. So BFS will be called with the tree node root, which is 50. Now root is not equal to null for this tree. So we'll declare the queue and we'll add 50 to the queue, right? Because why queue? Because we need to visit first in first out. Basically the first level we need to visit first. So the 50 added first and we want to visit it first. That capability queue data structure gives. That's why we use a queue in a breadth first search traversal or level order traversal. So we added 50 to the queue and it will go to this while loop till there is some node to be traversed. It means that there is some node in the queue to traverse. So we'll continue this while loop. We'll basically remove the node in a queue, basically the first come, first out. So which is the current. Current is basically now 50. We will print that 50. Level 0 we are printing first. Now is there a left child or right child? If the 50 has a left child and right child, add it to the queue. So we added left, which is 30. We added right, which is 60. So why have we added left first? We can add right also first, but generally we are traversing from left to right. So that's why we added left first. We want to traverse from right to left, then we can reverse these conditions. We can add the right child first so that it will be removed from the queue first. So now it will come back to the beginning of the while loop. It will remove the front of the queue, which is node 30. It will print the 30. It will basically push the left and right child of the 30, which is 20 and 40, and come back to the beginning of the while loop. It will basically remove the 60 from the queue. For 60, there are no left and right child, so it will not put anything to the queue. It will come back to the while loop. It will remove the 20 from the queue. So for 20, it will print. There is no left and right, so it will not enqueue anything to the queue. So it will again come back to the beginning of the while loop. It will remove from the queue, which is now print at 40. Now for 40 also there is no left and right child. So it will basically come back to the beginning of the queue. There is nothing pushed to the queue. Now queue is empty, so it will complete the while loop. And you can see we have visited all the nodes in a binary search tree in a level by level order, starting from the root as a first level. So we completed the different traversal techniques for binary search tree. The traversal techniques for binary search tree and binary tree are same. Only some points which are like Inorder Traversal for binary search tree gives the sorted output. That is the one additional property comes out as a part of Inorder Traversal of binary search tree. But implementation wise, the traversal techniques are same for binary search tree and binary tree. I will share the links of previous videos also in the description. Hope you understood the explanation. If you like the video, please share and subscribe. Thank you so much.